Hello, I'm Barbara Simons, and I'm going to talk to you about scheduling basic blocks. Well, the first question you might ask is, why should I care about instruction scheduling? The answer is that with the new processors that have come on the scene in the past few years, instruction scheduling has become increasingly important. In particular, a lot of the speed that these new processors have has been obtained by increasing parallelism in the processors. But people aren't going to be able to make use of this speed unless they know how to schedule instructions efficiently on the processors. And it's common knowledge that unoptimized code run on these processors does a lot worse than code which has been efficiently and well optimized. Throughout this talk, we're going to be interested in how to construct a minimum completion time schedule for a set of instructions. First of all, let's talk a bit about the models. In particular, as I've told you, I'm going to talk about basic blocks. So what is a basic block? It's straight line code with no conditionals. The idea is that a basic block is a chunk of code for which you know all of the code will be executed if any of it is. And so you don't have to worry about what may or may not happen. Let's look at an example. Here are 3 instructions, and let's suppose that we want to schedule these instructions. Now, in the first instruction, x is assigned a value. In the second instruction, y is assigned a value. And in the third instruction, z is assigned the value which is the sum of x and y. Now, it's clear that we can't execute the third instruction until we've executed the first 2. So, as we've observed, instruction 1 has to be completed before instruction 3 can begin. We represent this idea by representing instruction 1 and instruction 3 as nodes, and the fact that 1 has to be completed before 3 can begin as an edge from instruction 1 to instruction 3. So that just says we have to wait for 1 to finish before 3 can begin. So as I've said, we're going to construct a directed acyclic graph for basic block in which the nodes correspond to instructions and the edges correspond to data dependencies. Now let's look at some specific models. The first model we'll look at is a pipeline machine. So here we have a simple 2-stage pipeline. You can't get anything simpler than that and have it be a pipeline. The idea is that an instruction enters stage 1, and then it goes from stage 1 to stage 2. And we're always going to assume that the instructions take unit time. So we'll spend 1 unit in stage 1 and 1 unit in stage 2. If there's a dependence from one instruction to another, the second instruction must wait until the first instruction falls out of the pipeline. So if that first instruction starts at cycle 1, let's say, the second instruction can't start before cycle 3. Let's look at another example. Here we have a 5-node graph with nodes 1, 2, 3, 4, and 5. What happens when we schedule this graph in the pipeline? We can put instruction 1 in stage 1. There's no problem because there are no dependencies going into instruction 1. And then at the next cycle, we can move instruction 2 into stage 1, and instruction 1 moves into stage 2. The third cycle, instruction 1 falls out of the pipeline, and instruction 4 moves into stage 1. Now at the fourth cycle, we can put instruction 3 into the pipeline because as you'll notice, both instructions 1 and 2 have already fallen out of the pipeline, and instruction 3 is dependent on 1 and 2. In other words, there are dependencies from instructions 1 and 2 to instruction 3. And then finally, we can put instruction 5 in the pipeline because at the next cycle, instruction 4 has fallen out. Now what happens when we add an edge from instruction 4 to instruction 3 and try the same schedule? As before, we can start with instruction 1, followed by instruction 2, followed by instruction 4. No problems here. But if we next try to put instruction 3 into the pipeline, we can't do it because instruction 4 is still in the pipeline, and now because of this new edge, there's a dependence from instruction 4 to instruction 3, so we can't put instruction 3 in. Therefore, we have to introduce a unit of idle time because we also can't put instruction 5 into the pipeline because it too has a dependence from instruction 4. So we're forced to have a unit of idle time, and then we can put instruction 3 in, followed by instruction 5. Now, I'm sure you've realized that there are more clever ways of doing this. In particular, if we only start with instruction 4 instead of either 1 or 2, and then do everything else as before, by the fourth cycle, instruction 4 will have fallen out of the pipeline, and we'll be able to put instruction 5 in and then we can put instruction 3 in, and there will be no idle time. So it's clear that by starting with instruction 4, we could construct an optimal schedule, whereas if we start with instructions 1 and 2, we cannot. So this illustrates how the choice of the order in which you do your instruction scheduling can have an impact on how long it takes to schedule your instructions. Next, let's look at the latency model, which is going to look pretty similar to a pipeline model. Notice again we have, in this simple example, 2 stages. Now I should say this is an example for 0-1 latencies, which is, again, the simplest kind of latencies that you can have. In all of these cases, we're going to assume that you can have larger latencies or more stages in the pipeline, but for illustration, we're going to take very simple cases. So here we have the simple latency model with 0-1 latencies. It looks like a pipeline, except that we're going to let instructions fall out of earlier stages. In other words, they don't have to go all the way through. And that's the way we're going to represent the latencies. So let's see how we represent this with a graph, with a DAG. Now, if you see the DAG here with nodes A, B, C, and D, there are weights on the edges. So the edge from A to B has a weight 0, and the edge from C to D has a weight 1. These weights represent the latencies for the first edge. In other words, we're assuming that node A has latency 0, so both edges out of A have zeros on them. Node B has latency 0, so there's a 0 on the edge coming out of B, and node C has latency 1. So there's a 1 on the edge coming out of C. And if you think about how chips operate or processors, these latencies can come from the fact that we have to do certain kinds of instructions that take more time, like, for example, a load. So if you're going to do a load instruction, you usually have to wait for the value to be fetched from memory, and that takes more time than, say, just doing a simple add or multiply, or it can take more time. So again, let's look at how we might schedule this graph. If we schedule the nodes in the order A, B, C, D, so we start with node A, we can then schedule node B immediately after A because there's a latency 0 on the edge from A to B, which means that we don't have to wait after A has been finished to start B. We can then schedule node C immediately after B because we could have, in fact, started node C a unit earlier, but we can't have 2 nodes running at the same time. So we can schedule node C next. But now we can't schedule node D because there's a latency of 1 following node C, which means that we have to wait 1 unit of time after C has been completed before we can start node D. So that's what latency means. It means you have to wait the amount of time that the latency represents after the completion of the node. Again, we're assuming that the nodes or instructions all take unit processing time without the latencies. Now again, as you can see, there's a better way of doing it. Because node C has latency 1, we want to try to schedule it as early as possible in this case. So after scheduling node A, what we really want to do is schedule node C next, because we can then schedule node B to eat up the time that the latency of C is taking. And then when B is finished, we're able to start D immediately. Now let's look at classical scheduling theory. Actually, scheduling theory has been around for a long time, and there are a great many problems and areas that are covered by scheduling theory. And I'm only going to touch on one particular problem which is relevant to instruction scheduling, and that's the M-machine scheduling problem. So the idea in scheduling theory is that you have jobs that are run on machines, which you can think of as instructions that are run on processors. Again, it's the same idea, but there are there's different vocabulary for the different disciplines, which sometimes makes it a bit difficult for people in one to read the literature in the other. But in any case, this is the language of scheduling theory. And for this particular problem, we're going to assume that the machines are all the same. So we can schedule a job or instruction on any machine we want. Again, we're going to assume that the jobs take unit time. And as before, with instruction scheduling, we're going to assume that there's a directed graph, a directed acyclic graph that represents what's called precedence constraints or dependencies in the language of compilers. And that's, again, what the edges represent, and they're directed edges. So a job can run on any machine. All jobs have unit length. Unfortunately, and maybe not too surprisingly, This particular problem from classical scheduling theory is NP-hard. In other words, it's difficult to construct a minimum completion time schedule for an arbitrary input. Now, I want to emphasize that NP-hard involves worst-case analysis, and it doesn't tell you how things will do on average. But it does say that there is probably no efficient or polynomial time algorithm that will construct an optimal solution for all possible inputs. Now, finally, I just want to discuss briefly the assigned machine scheduling problem. This is back to looking at compilers again. Suppose we have, let's look at a particular example, the IBM Power 2. It's a processor which has 5 functional units with pipelining. It has 2 floating point units, 2 fixed point units, and a branch. Now, because these functional units have different operations, it's clear that you cannot schedule an instruction on an arbitrary functional unit. So if your instruction is going to be doing a floating point operation, it has to be scheduled on a floating point unit, likewise with fixed point. So it looks a little bit like that classical scheduling problem I was just showing you, but it's different in the sense that instructions or jobs, whatever you want to call them, are assigned to particular machines or functional units, or whatever name you use. It turns out that a very simple case of the assigned processor scheduling problem, or assigned machine scheduling problem, is VLIW scheduling, or very long instruction word. And the idea there is that you construct a schedule, as we've been doing all along, and you can think of each cycle as being represented by a word, where you have different chunks of the word represent different machines or functional units. So the first part of the word might be the name of the instruction that goes to functional unit 1, the second to functional unit 2, and so on. So these are fixed. So you're basically assigning instructions to functional units. And that's really what VLIW scheduling is. Now I want to discuss the difficulty of these problems. We've already mentioned that the scheduling problem for classical machine scheduling is NP-hard. Let's look at the pipeline and latency problems. If you recall, the latency problem looked a lot like a pipeline problem, and in fact, it is a lot like a pipeline problem. You can take a pipeline problem and model it as a latency problem, because the way the pipeline problem works is say if you've got a k+1 stage pipeline, you've got k+1 stages that every instruction has to go through. Now, if you instead want to look at that as a latency problem, where every node has unit processing time, the first unit, that first stage is represented by the processing time of the node, and then you can put weights of k on all the edges, which represent the latency, and it's still going to take k+1 units of time for the node to be completed before any of its successors can go. So basically, you can model the k+1 stage pipeline problem as a latency problem for latencies of size k. Therefore, we know that the latency problem for latencies of size k is at least as hard as the k+1 stage pipeline problem. This is because a latency problem can model more complicated things than a pipeline problem. Because remember, for the latency problem, you can drop out at any stage along the way. You don't have to go all the way through as you do with a pipeline problem. Now, it's known that the k+1 stage pipeline problem is at least as hard as the k-machine scheduling problem from classical scheduling theory. So what that tells us is that the latency problem is at least as hard as the pipeline problem, which is at least as hard as the classical scheduling problem, which is NP-hard. So we know that all of the problems that we want to solve, at least the ones we've looked at so far, are NP-hard. Well, that's kind of discouraging. The next question you might ask is, why should these be hard? Why should scheduling something optimally be hard? Let's look at another example. Here we have what looks like 2 graphs, but it's really one. It's really 2 disconnected components. And if we weren't trying to do this on a TV screen, we would put one on top of the other and make it more obvious to you that it's really one graph. So we have the numbered component and the lettered component. And what we want to do is to construct a minimum completion time schedule for this particular graph. Now, a standard technique which is used is to use critical path through the graph as a way of deciding what to schedule next. So if you look at the critical path in this graph, it's obvious that the critical path is in the numbered part of the graph. In other words, from, say, node 1 to 5 to 6 to 7. because that path has 4 nodes in it, whereas there's no path in the lettered graph with more than 3 nodes in it. So that means that nodes 1, 2, 3, and 4 all lie on critical paths through the numbered graph. So if you're going to use this approach, which is a reasonable approach to use, you're going to start by scheduling nodes 1, 2, 3, and 4. Now, I neglected to mention, let's assume that this is a 3-stage pipeline that we're scheduling it on. So that means after the 1 unit of time that the node takes in the schedule, we still have to wait 2 additional units to give it the 3 units to get through the pipeline. So after node 4, we cannot schedule node 5, but we can schedule node A. But now, you see, we can't schedule node 5 yet because we have to wait 2 units more after 4 has finished in that picture before we can start node 5. In other words, we have to allow 3 units total for node 4, which is starting from when it begins to when 5 begins. So we have to have a unit of idle time after node A before we can begin 5. Then we can put node B, because you'll see by the time 5 has finished, it will be 3 units from when A has started. So now we can put in node B. But again, now we have to wait, because we have to wait for 3 units after node 5 has started before we can start node 6. Once we put in node 6, we can put in node C, and then, as you'll see, nodes C, D, E, F, G, and H all look pretty much the same, and in fact, they're kind of filler. So we can just put them in arbitrarily and stick in node 7 somewhere, and we're done. But the problem is, the schedule that we've constructed has 2 units of idle time. But if we do something which is a bit counterintuitive and start instead with the lettered portion of the graph, starting with node A, we can then put in nodes 1 and 2, followed by node B. We can put node B in now because it will be 3 units of time after we started node A, because those units were taken up by A, 1, and 2. Then we can put in nodes 3 and 4. And now we can put in C and D, followed by 5, EF, followed by 6, and GH, followed by 7. And the schedule which we've constructed now has no units of idle time, and therefore clearly is optimal. Now, intuitively, what's happening here is that we have portions of each of the graph which are fat, where you've got a whole bunch of nodes that have no dependencies between them, and you're at liberty to take them as you wish and intersperse them around among the schedule. And we also have a portion of each graph which looks kind of like a chain or just a path. And that part is much more constrained because we have to have units of idle time between each of those nodes. And so what we really want to do is to take these 2 chunks and sort of slide them around each other, slide one above the other, and use the fat part as sort of fill within the chain. Now, this isn't a very scientific explanation, but intuitively that's what we want to do. And the problem is that if you use any kind of heuristic which is dependent on, say, critical path or something like that, you're going to lose this notion of sliding components across each other to make use of the fluff or the fill. Now let's look at another problem. Again, this is looking at some of the hardness issues. We've been talking about scheduling instructions on functional units in processors, but in fact processors also have registers. And whenever you do instruction scheduling, you also have to worry about the registers. So let's look at a very simple graph. Again, this is one graph, even though it looks like a whole bunch of graphs, where each component of the graph is a chain, or you can think of that as being like a thread in a program. So we have these sets of chains, and we want to schedule all of them at the same, altogether to construct a minimum completion time schedule. And let's assume that we also have one register. Some of the nodes are assigned to the register and others aren't. We want to schedule this on a single processor where we have latencies of 0 or 1. So remember now, we've got one processor, 0, 1 latencies, one register, and a DAG, or dependence graph, which is only a set of chains, a very simple kind of graph. It turns out that constructing a minimum completion time schedule for this very simple problem is, again, NP-hard. And the thing that makes it NP-hard is that register, because the same problem without the register is very easy to schedule. So from that, we can conclude that, not too surprisingly, almost all mathematically abstracted scheduling problems are NP-hard. And unfortunately, real-life scheduling problems are even harder. But remember, NP hardness is a notion which applies to worst case analysis when you want to construct an optimal solution to a problem. In reality, we don't usually insist that something be optimal. And in particular, worst case is something which doesn't occur very often. At least you certainly hope it doesn't. So in fact, reasonable heuristics usually construct pretty good schedules. And in fact, we even have some mathematical results to that effect. So let's now look at heuristics. The first heuristic I want to discuss is what's called list scheduling. In fact, it's so simple-minded that it's almost not worth even being called a heuristic. The idea is that you take all of the instructions and you put them into a list in some way. And then you use this list to construct a feasible schedule, again, in some way. Now, as I say, this is pretty simple-minded, and the only reason I'm even mentioning it is that it's used by most algorithms in heuristics that you would be interested in that are related to instruction scheduling. Of course, the trick with list scheduling, as I'm sure you realize, is in how do you construct the list. Now, greedy scheduling is a variant on list scheduling. For greedy scheduling, you assume you are given a list. Again, we aren't saying how we're constructing it yet, because that's really the tricky part. Somehow you're given a list, and what greedy scheduling does is it always selects the first available instruction to be scheduled whenever it can. In other words, as you go along constructing your schedule, you always take the first instruction from the list, which is available to be scheduled and has not yet been scheduled, and you choose that as the next instruction to be scheduled. And one of the characteristics of greedy scheduling is that it never allows idle time to exist on a functional unit or processor if there's any instruction which is available to be scheduled. Now I want to talk to you about highest level first scheduling, which is actually a heuristic which takes advantage of the structure of the dependence graph and uses that structure as a way of constructing the list, which is then going to be scheduled greedily. Now, again, we're going to assume, as we have all along, that each node or instruction takes unit time, that we have weights on the edges, which, again, are going to represent the latencies. And what we're going to do is we're going to construct a layered graph, which is going to represent the distance between a pair of nodes, the distance of the longest path between a pair of nodes. Now let's look at this example with nodes A, B, C, D, and E. And let's see how we can construct a level or a layered graph for this example. Now remember, we're trying to do something for a heuristic which is called highest level first. And so intuitively, we want the nodes that we want to put first in our list, or what we expect to be first on our schedule, to be at the highest level. So the node we're going to put at the bottom is the node which is going to have to go last in this case, which is node E. So we're going to start with node E at level 0. And now there's an edge from node D to node E with weight 1, and an edge from node C to node E with weight 1, or latency is 1. So remember now, what latency means is we have to wait 1 unit of time from when node D completes to when node E can begin. And we represent that delay by skipping a layer or a level in the layered graph that we're constructing. So if we put node E at level 0, or layer 0, we're going to put both nodes C and node D at level 2. So we skip a level in between nodes D and C and node E. Now we have node D at level 2. We can put node B at level 3 because the edge from B to D has weight or latency 0, and therefore we don't have to pause or wait after B has been completed and before we start D. So now we have 4 of the nodes in our level graph, and all that remains is to add node A. Well, there's an edge with weight 1 from A to B, but the real problem is the edge with weight 3 from A to C. So that means, again, we're going to have to skip 3 levels between C and A. Since C is at level 2, then we have to skip 3 levels. We find that we put A at level 6. And now we have our level graph. And the levels represent the lengths of the longest paths in the original graph between pairs of nodes. So the fact that A is at level 6 and E is at level 0 means that there is a path of length 5 between A and E. And if you look at the graph, you can see that, because after A completes, we have to wait 3 units of time for the latency on the edge AC, plus 1 unit for C itself is 4, plus 1 unit for the edge CE, which is 5, before we can start node E. Now, let's just take this level graph and read the nodes off of it and construct an ordered list. So A is clearly going to be first. It's the node which is at the highest level. B will be second. And then we have C and D both at level 2, at the next level. So let's suppose we put C first and then D, and then we follow that by node E. So now we have a list, and now we're going to schedule that list greedily. So we always can start with A because it has no edges coming into it. And now we have to wait 1 unit of time after A finishes before we can start B because we have a latency 1 from A to B. Now we can start D immediately after B. And now we can start C because even though there's a latency 3 edge from A to C, as you can see, there are 3 units in between A and C which are occupied either by other instructions or by idle time. And now we have to wait 1 unit of time after C completes before we can start a node E or instruction E. And in fact, that is an optimal schedule, although you don't necessarily always get optimal schedules using highest level first. Notice in this example, the order of the instructions or the nodes in the final schedule is not the same as the order in the ordered list. Now, you could say, but of course we made an arbitrary choice in the ordering between C and D, and that's true. But we could look, there are other examples we could look at where the choice isn't arbitrary and we still end up with a different order in the final schedule. So, as I mentioned earlier, heuristics tend to perform fairly well in practice on these problems. And now I want to discuss some of the mathematical results that we have that support that claim. It turns out that greedy scheduling, now this is greedy scheduling without even using the cleverness of highest level first scheduling. So just plain ordinary greedy scheduling is guaranteed to construct a schedule with a completion time that is no worse than a factor of 2 of optimal for the following problems. M identical machines with no latencies. This is the classical scheduling theory that I was talking about before. So basically, even though we know that problem is NP hard, we know that any greedy scheduling heuristic is guaranteed to construct a schedule with a completion time no worse than 2 times the optimal completion time. The same holds true for scheduling a single pipeline with k stages, or M identical machines, not pipelines, but machines with arbitrary latencies. All right, we know that the greedy scheduling heuristic will do reasonably well, or at least is guaranteed not to do terribly for the problems that we just mentioned. And it would stand to reason that highest level first will do even better. And in fact, if you were going to be constructing a heuristic for scheduling problems on any of the machines that we just talked about, any of those kinds of machines, I would certainly urge you to use highest level first and not ordinary greedy. However, we do have a fairly negative result, actually strongly negative result on highest level first for the following problem. We have the assigned processor scheduling problem with M processors. For that problem, we know that the highest level first heuristic can construct a schedule with a completion time that is almost M plus 1 times worse than optimal. Now, this is actually somewhat discouraging, both because assigned scheduling is something that we want to do in practice. If you recall, for the Power 2 example, a real-life processor has an assigned scheduling problem associated with it. But again, I want to reiterate that this is a theoretical result, and in order to get this kind of bad behavior, you always have to make the absolutely wrong choice. Whenever you're given choices, you choose the dumb thing. And if you tweak the problem slightly, you're not going to be able to get such a bad result. So finally, I want to talk a bit about algorithms, because there are certain cases where we can construct optimal schedules efficiently, at least for relatively simplified models of these problems. So the first problem I want to look at is the problem of trees, in particular either in trees or out trees. So an in tree is a tree in which all of the edges are going towards the root, and an out tree is one in which they're all going away from the root. Now again, a problem from classical scheduling theory says that if you have m identical machines and your directed acyclic graph is a forest of either in-trees or out-trees, and you have unit time instructions, then constructing a minimum completion time schedule is easy to do. It's efficient. In other words, it's polynomial time. Now this particular result carries over rather directly, actually, to the problem of scheduling pipelines where each pipeline has the same number of stages, namely some value k. So if you have m identical k-stage pipelines, then again, you could construct an optimal completion time schedule in polynomial time in a rather straightforward way, actually. Another well-known scheduling problem is the classical scheduling problem for two identical machines. Now, I've told you that if you have an arbitrary number of identical machines, namely m of them, that the problem is NP-hard. However, if you have only two, then there are two polynomial time algorithms that are known for that problem. And in fact, they both carry over to pipeline scheduling. So, and they both carry over directly. So you can take both of those algorithms from classical scheduling theory and apply them to this two-stage pipeline problem without even making many modifications to them. As an aside, I'd just like to mention that the three-machine scheduling problem from classical scheduling theory is the major open problem in scheduling theory. And nobody knows if that problem is, if constructing a minimum completion time schedule for that problem is NP-hard, or if there's a polynomial time algorithm for it. And that problem has been around for quite a while, and it hasn't yet been cracked. So now let's look at the latency problem, where you have latencies of 0 and 1. Now remember, this is a more complicated problem than the two-stage pipeline problem, because instructions can drop out after the first stage or go through to the second. There are two known algorithms for solving this problem optimally on a single machine with unit time instructions. The first is, again, similar to one which is known from classical scheduling theory. The second, which also can deal with time-critical instructions, which is something which would be quite useful if you're having to do instruction scheduling with real-time constraints, is one of the few examples I know of which does not have a comparable result from classical scheduling theory. I expect that as we continue working in these problems, we'll come up with more cases of problems which are related to instruction scheduling and do not derive from classical scheduling theory. Now, both of these algorithms for 0-1 latency can be used as heuristics for the kinds of problems that we really do want to solve, namely where we have larger latencies, or perhaps we have instructions that require unit time, or we have multiple processors, or even if we have assigned processors, or functional units, I should say. Now, again, these are going to be heuristics. We can't promise you optimal solutions. In fact, in general, you will not get optimal solutions, nor do we even have mathematical results which will tell you how well these will do in general, aside from the fact that both of these heuristics use greedy scheduling, and so the results from greedy scheduling carry over. However, it's quite likely that in most cases, the heuristics which go into more detail about the graph structure, which is true for both of the 0-1 latency heuristics, will perform better than the more simple-minded heuristics for most of the kinds of problems that we're looking at. And now, Vivek Sarkar will tell you how to schedule loops.
Hi, I'm Vivek Sarkar, and I'd like to talk to you about instruction scheduling for loops. The reason this is an interesting subject is because basic blocks just do not provide sufficient instruction parallelism for the kind of superscalar processors being built today. This has been observed by many researchers, and for instance, I'd like to share with you a quote from a textbook by John Hennessy and Dave Patterson, in which they say, "Loop unrolling, trace scheduling, and software pipelining all aim at trying to increase the amount of local instruction parallelism that can be exploited by a machine issuing more than one instruction on every clock cycle. The effectiveness of each of these techniques and their suitability for various architectural approaches are among the most significant open research areas in pipeline processor design." The thing that I find interesting about this subject is that I've been working with loop transformations in IBM for a variety of purposes, for shared memory parallelization, distributed memory parallelization, vectorization, improving data cache locality, and it's quite fascinating to see how some of these same techniques can be used to improve instruction-level parallelism. Of the techniques referred to in the textbook by Hennessy and Patterson, I will be covering loop unrolling and software pipelining today. Let's start by looking at the loop unrolling transformation for an innermost loop. In this transformation, we start with a do loop that's written in a Fortran style notation, where you have one copy of the loop body and you have an index variable I that goes from a lower bound to an upper bound. And what's actually performed in this transformation is that you make multiple copies of the loop body. The loop is said to be unrolled with a factor of r if you make r copies of the loop body. Now what you have is a loop with a larger loop body, r copies of the original loop body, and a remainder loop to take care of the case when r does not divide the number of iterations evenly. This simple transformation can result in many optimization benefits. It can improve the amount of instruction parallelism in the loop body. It can also improve the register reuse and locality. And one that is getting less important these days, but still can be useful, is that it decreases the amount of loop overhead. So let's try and understand this optimization better by looking at an example. Consider a simple loop with a vector operation. There are two adds and a multiply and a store. There are also three loads for fetching the three input arguments. You can assume that the scalar variable e stays in a register throughout the lifetime of this computation. Now, the first thing we would do with an example like this is build a dependence graph for the basic block. As you've seen before, we have a dependence graph in which the nodes are instructions, and we assume that each instruction takes unit time. The edges represent dependencies, and each edge is labeled with a latency value of 1 in this case. Now, in this example, we have a dependence graph that can drive a compiler writer crazy, because what we see is a chain of dependencies that goes from a load to the first add, the result of which feeds into the second add, the result of that feeds into the multiply, and finally into the store. So we have a very long critical path length, and even an optimal schedule for this basic block would have a lot of idle cycles. In fact, we can see that if we were to lay out a schedule for a machine like the IBM RS6000, where there is a fixed point unit and a floating point unit. The three load instructions would have to be scheduled first on the fixed point unit, and then the first add has to wait for at least two load instructions to complete. The second add has to wait for the first add instruction to complete. The multiply has to wait for the second add, and finally we get to the stored instruction, which needs a slot in both the fixed point and the floating point unit. The elapsed time for this entire schedule is 10 cycles, and as you can see from the picture, there are many idle cycles in this schedule. Now let's take a look at what would happen if this basic block was enclosed in a loop, as I'd shown you earlier. Now we get some benefit from the smarts that are put in by the hardware. Most modern processors have the ability to look ahead, which is to dispatch instructions that go beyond the branch at the end of a loop. In this case, what would happen is the three load instructions from the next iteration can actually be executed while the computations of the current iteration are proceeding, because there are no dependence constraints. So what we would see now in the steady state, and this is purely by hardware smarts, this is not by changing the schedule in the compiler at all, is a schedule in which the three loads for the next iteration are overlapped with the two adds and the multiply and the store for the current iteration. This leads to a steady state in which the execution time is 7 cycles per iteration. And that's a significant improvement over the 10-cycle schedule that we had seen for scheduling a basic block. But yet, we do see those idle cycles in there. And here's where loop unrolling can be useful. Now, the loop unrolling transformation, when applied to this example, if we were to unroll with a factor of 2, would result in 2 copies of the loop body, one for I and one for I plus 1. Now, this example has a nice property that the loop is a parallel loop, or is also known as a vectorizable loop, because it has no loop carrier data dependencies. When we make 2 copies of the loop body, one for I plus 1, what we are accomplishing is we're getting a larger set of independent instructions because the iterations do not have any data dependencies among them. Specifically, if we were to lay out the schedule as we had seen earlier in this case, we would be able to issue the add from the current iteration, from the first copy of the iteration, then the add from the next copy, the I+1 copy, back to the second add from the first iteration, then the second add from the second iteration, and so on. And this interleaving very nicely fills in all the idle slots in the schedule. The loads would go ahead and fetch the operands for the next iteration, but they too will fill out all the idle slots in the schedule after loop unrolling. So the result is an optimal schedule, and this is easy to see because there are absolutely no idle slots in the schedule. The fact that loop unrolling can lead to improved performance has been observed several times in the past by different researchers, and it's well known among people in the industry, compiler writers in the industry, that this can be useful. However, for some reason there have not been a sufficient number of systematic studies done. One study that's been good in this respect was performed in 1987, where Weiss and Smith simulated the execution of the first 14 Livermore loops on a Cray architecture. What they did was they unrolled each of the loop kernels by factors of 2, 4, and 8. And then they measured the speed up that would be obtained in this case. So what they observed in their study is that an unroll factor of just 2 can yield an improvement, an average improvement that's in the range of 36 to 39%. An unroll factor of 4 can give an improvement that's in the range of 57 to 63%, and an unroll factor of 8 can give an improvement that's in the range of 68 to 76%. Now, one catch in this, in obtaining these speedups is that successively larger unroll factors require larger amounts of registers to deliver the extra performance. An unroll factor of 2 required 18 registers, an unroll factor of 4 required 37 registers, and unroll factor of 8 required 73 registers. So even though loop unrolling has been shown to deliver good performance improvements, people have found that too much unrolling can be hazardous to your health. Let me explain. There's a phenomenon known as register spills. If the unrolled loop body requires more registers than your hardware has available, the compiler is forced to generate extra load and store instructions that transfer data back and forth from the registers to the main memory. So in the example I'd shown you earlier, when we unrolled the loop with a factor of 2, if for some reason we only had 8 registers available, we would have been forced to introduce a register spill because there were 9 values that need to be stored in registers. 4 values for the arrays A, B, C, D in iteration I, 4 values for iteration I+1, and a 9th value for the scalar variable E. Now let's take a closer look at this phenomenon. Is it really the fault of loop unrolling that there's a degradation when large unroll factors are used? In actual fact, an unrolled loop body should be able to use the same number of registers as the original loop body. There always exists a schedule in which the copies of the loop body can be arranged contiguously so that the same set of registers is reused for each copy. So it's really not the fault of loop unrolling that we see this degradation. Instead, it's a comment on the fact that we do not as yet have a robust integrated algorithm for both instruction scheduling and register allocation in compiler theory. So to summarize this discussion on unrolling an innermost loop, the problem that we need to solve is to find an optimal unroll factor R opt such that the speedup is maximized if we consider all the benefits from instruction parallelism, and also such that the unrolled loop does not introduce any more register spills per iteration than the original loop body. As I mentioned earlier, this is because of the lack of an integrated algorithm for register allocation and instruction scheduling. When compiler theory advances to that point, we can in fact drop the second constraint from the problem statement. Let us now move to looking at loop unrolling in a wider context, and that of unrolling multiple loops. When we look at multiple loops, an interesting question to ask is, what does it mean to unroll an outer loop? In the figure that I have over here, if we unroll the outer loop I1, literally, we would obtain 2 copies of the inner loop I2. Now that in itself does not deliver any performance improvement from an instruction level parallelism point of view. However, if we were to jam the 2 loops together, we would obtain a combined loop body with 2 copies, one for index value I1 and one for index value I1 plus 1. This unroll and jam combination is really what I mean by unrolling an outer loop. Now, an interesting fact about unrolling outer loops is that there are cases in which it may be illegal to perform the transformation. We did not have this problem when unrolling an innermost loop because the unrolling transformation just performs the iterations in the same order that they would have been executed anyway. However, unrolling an outer loop in the manner that I've shown can actually change the order in which loop iterations are performed. Take a look at this example. In this example, we see that for iteration 2 of the inner loop I2 and iteration 1 of the outer loop I1, the computation writes into array location A2, 1. And then later on, for iteration 2 of the outer loop I1 and iteration 1 of the inner loop I2, the same value is read. From a theoretical point of view, when we look at loop transformations and data dependencies, this combination of a write followed by read is referred to as a flow data dependence with distance vector 1, -1. However, if we were to unroll the outer loop in this case, what we would obtain is 2 copies of the loop body for values I1 and I1 plus 1. And in the first iteration of the inner loop I2, we would see a case where the read of A21 is performed before the write occurs. What this means is that the read can actually fetch a value that is undefined or is at least incorrect. So this is an example of illegal unrolling. Fortunately, there's a very simple rule to tell us when it is legal to unroll an outer loop. It is legal to unroll an outer loop I sub j if it is legal to permute it to the innermost position. This relates loop unrolling to the loop interchange transformation and results in a simple rule that can tell us which loops in a perfect loop nest can be unrolled. So in general, the idea of unrolling outer loops can be applied to an entire nest of loops where the outermost loop I1 can be unrolled with the factor R1, the next loop I2 can be unrolled with the factor R2, and so on. And then you get a composite loop body with as many copies as the product of all the unrolled factors. An interesting phenomenon that arises with unrolling outer loops is that of register locality. And here what we see is that the speed up that you obtain from unrolling can also depend on the amount of register reuse carried by the individual loops. In the example that I have, we see that the outer loop I1 carries register reuse for arrays B and C, and the next loop I2 carries register reuse for C. What does it mean to say that loop I1 carries register reuse for arrays B and C? What it means is that for multiple copies of the I1 loop, the same elements of arrays B and C are accessed. When they are fetched from memory into a register the first time, the same register can be reused again for multiple copies of the I1 loop. And this is a savings and leads to an additional speed up because you eliminate load instructions that would have been executed otherwise. So to summarize this discussion of outer loop unrolling, what we really want to do is to look at a perfect nest of loops and try and find an optimal set of unroll factors for each of the enclosing loops, R1 to Rk, such that if any unroll factor is greater than 1, we make sure that it is indeed legal to unroll that loop and the speed up is maximized. As before, we'll carry forward the constraint that the unroll loop body should not have any more register spills per iteration than the original loop. Now I'd like to switch to another loop transformation that's very important for instruction parallelism, and that is software pipelining. The basic idea in software pipelining is a little different from loop unrolling. The goal here is to try and get the maximum overlap between different iteration instances of instructions. So what you do in this case is rather than make multiple copies of instructions, you have a transformed loop in which there is exactly one copy of the original instructions, but each of the instructions have been shifted in the iteration space by some offset. so that instruction 1 could be executing its instance corresponding to offset 1, instruction 2 could be executing its instance corresponding to offset 2, and so on. And this allows you to exploit the parallelism that there is among different iterations, even though there may be a long chain of dependencies within a single iteration. Let's take a look at an example to understand this better. If we take the same example we worked with earlier for loop unrolling, what software pipelining would do is offset the instructions differently. The way this would work is that you'd have the store from one iteration, the multiply from another iteration, the add from another iteration, all performing concurrently. If you look at how the schedule gets laid out on an RS6000 machine, you'd see the store from iteration I-3, let's say, the loads, and then the multiply from iteration I-2, and add from iteration I-1, and finally an add from the current iteration. And since all these instructions are from different iterations, they can actually be executed concurrently. All the pipeline slots get filled, and there are no idle cycles. And in fact, this schedule also delivers a performance of 4 cycles per iteration, which is exactly what we got with loop unrolling. Software pipelining has 2 important advantages over loop unrolling. One is that the generated code is more compact. You just have one copy of all the instructions in the software pipeline loop. This is important from the point of view of compile time, and also if you're really working with a large loop, it may be important from the point of view of the instruction cache size limitations. The second advantage is that the overhead due to startup and shutdown, when there may be less amount of parallelism available at the beginning and at the end of a schedule, is relegated to the prologue and the epilogue outside the loop boundary. However, loop unrolling also has 2 important advantages over software pipelining. The first advantage is that it can be applied to multiple nested loops. As yet, no one has developed a theory for software pipelining in a perfect loop nest with multiple loops. All the software pipelining results apply only to the innermost loops. The second advantage, which is also important, is that loop unrolling places no constraints really on what's inside the loop body. The loop body is allowed to contain conditionals, whereas software pipelining can only work if the loop body does not contain conditionals. In the same study that I referred to earlier, Weiss and Smith also studied the software pipelining transformation, and what they found on those Livermore loops was that software pipelining could also deliver an improvement in the range of 27 to 29%, which is just a little less than the improvement obtained by unrolling the loops by a factor of 2. The conclusion of their study was that software pipelining delivers a slightly lower speedup than loop unrolling, but also demands fewer hardware resources, like registers and the size of the instruction cache required. I'd now like to share with you an important theoretical foundation for software pipelining. This is called integer periodic schedules, and this was developed by Reiter in 1968. An integer periodic schedule is one in which the start time of the kth instance of an instruction goes in a fixed period denoted by the initiation interval II and has a fixed constant offset, which can be different for the different instructions. Given this framework for integer periodic schedules, the problem that's interesting to solve is to try and find a schedule that has the smallest initiation interval, II, because what that means is in the steady state, you'll get the maximum throughput and the maximum speedup if the initiation interval is minimized. The interesting result in Reiter's paper is that he could actually provide a closed form formula for what's called the maximum cycle ratio of a data dependence graph. And this is computed as a function of all the cycles in the data dependence graph and the latency across the cycles and also the iteration distance across the cycles. And he could prove that the way you get the smallest initiation interval is by finding the maximum cycle ratio among all cycles. An interesting property of this result is that you do not actually need to enumerate all cycles in the graph to find this optimal solution. You can in fact just use a polynomial time algorithm to come up with an initiation interval that accomplishes this maximum cycle ratio. So to summarize this discussion on software pipelining, we see that an optimal software pipeline can be found in polynomial time if you're working with an unbounded number of resources. which is an easier problem. But if we really want to solve the practical case of a bounded number of resources, like limited number of functional units or pipeline stages, the problem does become NP hard. What I expect to see coming out in the future is a combination of the loop unrolling and software pipelining transformations so that you can merge the benefits of both when instruction scheduling for loops. Finally, I'd like to address some data cache issues in these loop transformations for instruction scheduling. If you're unrolling an innermost loop or performing the software pipelining transformation, actually you don't have to pay too much attention to the data cache because the memory references are generated pretty much in the same order as they would have been generated in the original loop. And so we have a low impact on the data cache locality. Essentially, the transformed version of the code has the same working set as it did in the original version. However, unrolling an outer loop can be a different matter. There is indeed a potential for a large impact on data cache locality. Let's look at an example to understand this. Consider a simple example where you have a vector add computation. You're adding b sub j comma I to a sub I. In the original version of this loop, the elements of array B would be accessed in linear order in memory. Now this unit stride has a very good property in terms of data cache locality. On average, you're going to have a cache miss, say, every 8 iterations if your cache line size contains 8 words of the array B. Now let's consider what would happen if we were to unroll the outer loop I. You'd get 2 copies of the loop body, one for I plus 1. And in the j equals 1 iteration, you'd be accessing 2 elements of array B, B1, 1 and B1, 2. The danger here is that these 2 elements are spread far apart in memory and could potentially displace each other in the cache. In general, when you have a larger loop, or if you're unrolling an outer loop by a larger factor, this effect can be more pronounced. And what would happen in such a case is that the second array access could actually displace the cache line containing the first access from the cache, so that when you go to the next iteration of the inner loop j, you're not going to find it in cache anymore. And in the worst case, there can be a cache miss for every memory access. This can cause a terrible slowdown. So to conclude our lecture, we see that scheduling is required to efficiently use modern processors. What we've done today is we've surveyed scheduling techniques and hardness results for scheduling basic blocks. We've shown you that loops are where the action is in terms of fully exploiting the instruction level parallelism available in today's hardware. And then we examined the effect of the loop unrolling and the software pipelining transformations on instruction parallelism. So remember, don't waste those cycles. I hope this lecture has helped you understand instruction scheduling better in the context of basic blocks and loops. Thank you very much.